morning, my dear students. Today I will explain you about the basic concept of aromaticity, Huckel rule, and applications to benzenoid and non-benzenoid compounds. Concept of aromaticity. Aromatic compounds are cyclic and planar. Usually, these aromatic compounds undergo substitution reactions rather than addition reactions. Usually, unsaturated hydrocarbons undergoes addition reactions, but here aromatic compounds, they are high level of unsaturation even though they undergoes addition reactions. So this particular property is common to all aromatic compounds, and this particular property is referred to as aromaticity or aromatic character. Particularly this aromatic character is due to extensive delocalization of pi electrons in planar ring system. Huckel rule. According to this rule, all aromatic compounds must have 4n plus 2 pi electrons, whereas n is a whole number, that is its value may be 0, 1, 2, 3, 4, so on. This rule is known as 4n plus 2 pi rule or Huckel's rule. It is discovered by Erich Huckel in 1931. According to Huckel rule, the number of pi electrons in aromatic compound may be 2, or that means n value 0, or 6 if the n value is 1, 10 if n value is 2, 14 if n value is 3, and so on. In benzene, the n value is 1. That means it contains 6 pi electrons. This Huckel rule is not applicable to non-aromatic compounds, even if it has cyclic and planar in nature. So this is Huckel rule. Huckel rule is 4n plus 2 pi electrons if n value 0, 1, 2, 3, 4. For example, if n value is 0, the 4n plus 2 value is 2. Just like if n value is 1, 4n plus 2 value is 6. If n value is 2, 4n plus 2 value 10. Like that, these 2, 6, 10, 14, 18. These are called Huckel series. So if the n value is 0, the Huckel series value is 2. Like that, we can calculate the aromatic character in benzenoid and non-benzenoid compounds. See, in this slide, benzenoid compounds. Usually, aromatic compounds containing benzene ring are known as benzenoids. For example, the parent ring is benzene. So in this structure, benzene is cyclic and planar. It has p orbital on each carbon of the ring, involved in double bond or extensive delocalization of pi electrons in planar ring system. It has 3 double bonds. That means 6 pi electrons. According to Huckel rule, 4n plus 2 is equal to 6 pi electrons. So n value is equal to 1. N is Huckel series number, so it is aromatic. So benzene is aromatic compound. So it satisfies Huckel rule. See this. This is benzene ring. The structure is cyclic and planar, and it has 3 double bonds. It is in conjugated. In this structure, one double bond contains 2 pi electrons. Here 3 double bonds are there. So 3 double bonds means 6 pi electrons. So 6 pi electrons means it obeys Huckel's number. So benzene is aromatic in nature. The second example is naphthalene. Here there are two benzene rings are fused It is also cyclic and planar. It contains p orbital on each carbon of the ring involved in a double bond. In the naphthalene structure, there are 5 double bonds. 5 double bond means each double bond contains 2 electrons. Total 10 pi electrons. According to Huckel rule, 4n plus 2 is equal to 10. So 4n value is equal to 8. Therefore, n value is equal to 2. So this is also aromatic compound. The next one is non-benzenoid compounds. Aromatic compounds and those not containing benzene ring are known as non-benzenoids. Example, cyclopentadienyl anion. In this structure, there are 2 double bonds and 1 lone pair of electrons. So it is also a cyclic and planar structure. It is completely conjugated. Moreover, it has 2 double bonds and 1 lone pair involved in delocalization. According to Huckel rule, 4n plus 2 is equal to 6. So 4n value is equal to 4. So therefore n value is equal to 1. So it is also a Huckel number. So it obeys Huckel law and hence it is aromatic compound. This is cyclopentadienyl anion. The structure is cyclic and planar. It has conjugated structure. It has 2 double bonds. 2 double bonds means 4 pi electrons and 1 negative charge, that means 2 pi electrons. Total 6 pi electrons. So 6 pi electrons means it is Huckel number. So cyclopentadienyl anion also a aromatic compound. Second example, cyclopropenyl cation. Here in this ring there are 3 carbon atoms in cyclic manner and moreover it has 1 positive charge. So it is cyclopropenyl cation. It is cyclic and planar. It is completely conjugated and it is 1 double bond, that means 2 pi electrons involved in the delocalization. According to the Huckel rule, 4n plus 2 is equal to 2 pi electrons. So 4n value is equal to 0. So therefore n value is equal to 0. So it is also a Huckel number. Hence it is also aromatic compound. The third example is cycloheptatrienyl cation. It is also called tropylium cation. It is cyclic and planar. It is completely conjugated and it has 6 pi electrons involved in delocalization. According to Huckel rule, 4n plus 2 is equal to total 6 pi electrons because in this structure there are 3 double bonds. So 4n is equal to 4. So therefore n value is equal to 1. Hence it is also aromatic compound. My next concept is general mechanism of electrophilic aromatic substitution reactions. So in this session I will explain about Friedel-Crafts alkylation, Friedel-Crafts acylation, halogenation and nitration. So in this given picture, the container has benzene ring. So benzene usually undergoes electrophilic substitution reactions. Even though it has unsaturation, it not involved in addition reactions. So this particular property is called aromatic character. So usually benzene electrophilic reactions are halogenation, nitration, sulfonation, alkylation and acylation. Let's start this mechanism with a general mechanism of electrophilic aromatic substitution reaction. Electrophilic substitution reactions in benzene. In benzene, each carbon atom undergo sp2 hybridization. So the benzene ring with its delocalized pi electrons is in an electron rich system, so it is attacked by electrophiles giving substitution products. So these reactions can be represented as, in the given equation, benzene, when it reacts with a reagent, it contains both electrophile and nucleophile. In the presence of catalyst, substitution takes place. It gives substituted product. So this reaction, for our convenience, it can be explained with the help of mechanism. It has 3 steps. The first step is formation of an electrophile. In the presence of catalyst, the reagent is dissociated to give electrophile and nucleophile. In the alternative second step, the electrophile which is formed in the first step, it is ready to attack on the aromatic ring to form a carbonium ion. So this is carbonium ion. The intermediate ion is resonance stabilized. It is a hybrid of the following 3 structures. Finally, in the third step, loss of proton by carbocation gives substituted product. So this is the general mechanism. It is common to all type of electrophilic substitution reactions. Let's start with our reactions with Friedel-Crafts alkylation. So Friedel-Crafts alkylation, benzene reacts with alkyl halides in the presence of aluminum chloride to form alkyl benzene. So here aluminum chloride is Lewis acid. In this equation, benzene reacts with methyl chloride. Here methyl chloride is alkyl halide. So this alkyl halide reacts with benzene in the presence of catalyst AlCl3 aluminum trichloride. It gives toluene. This is also called methyl benzene. So this reaction can be explained with a suitable mechanism. So the mechanism follows 3 steps. Step 1, formation of electrophile. Electrophile here is CH3+. So in the first step, the reagent reacts with a catalyst dissociate to give an electrophile and AlCl4. So this CH3+, it attacks on the benzene ring to give carbonium ion in the second step. So in the second step, benzene, it is reacts with CH3+. That means the electrophile attacks on the any of the hydrogen. So it attacks on the benzene ring to give carbonium ion. Finally, this carbonium ion loss a proton give alkyl benzene. So it is also called methyl benzene or toluene. So this is the reaction of Friedel-Crafts alkylation. The next one, Friedel-Crafts acylation. Friedel-Crafts acylation, benzene reacts with acetyl chloride or acid chloride in the presence of AlCl3 aluminum chloride to give aromatic ketone. For example, benzene when reacts with acetyl chloride in the presence of aluminum chloride, it gives aromatic ketone. So this aromatic ketone is acetophenone. So this particular reaction can be explained with the help of a mechanism. It has 3 steps. In the first step, the electrophile generation. Here acetyl chloride when reacts with catalyst aluminum chloride it gives acetyl carbonium ion. In the next step, the acetyl carbocation, which acts as an electrophile, this attacks on the benzene ring to form a carbonium ion. So this carbonium ion, finally it lost a proton, gives an aromatic ketone. Here aromatic ketone is acetophenone. Third one, halogenation. Benzene reacts with halogen like chlorine or bromine in the presence of ferric chloride or aluminum chloride at room temperature to form chlorobenzene. Mechanism. It involves the following steps. Step 1. Formation of the electrophile. In the first step, the reagent reacts with ferric chloride to give electrophile chloronium ion. Here Cl plus is electrophile. So the chloronium ion attacks on the benzene ring to form carbonium ion. In the third step, loss of proton yields chlorobenzene. Nitration. Nitration means benzene reacts with concentrated nitric acid in the presence of concentrated sulfuric acid at about 60 degrees centigrade to form nitrobenzene. Here concentrated nitric acid and concentrated sulfuric acid is called nitration mixture. So benzene here reacts with nitric acid in the presence of concentrated H2SO4, gives nitrobenzene. So the reaction contains 3 steps. In the first step, formation of electrophile nitronium ion. So in this step, the concentrated HNO3 is going to react with sulfuric acid, gives NO2 plus, that is electrophile. In the second step, the electrophile attacks the benzene ring to form carbonium ion. In the final step, the carbonium ion lost a proton to form nitrobenzene. So this is the reaction of nitration. Thank you.